proof of the derivative formula for all rational values of n. So we first proved at the beginning by first principle. To prove this formula, you have to let f of x equal to x power n. Now remember, n is a positive integer, so that means if you want to find the derivative, you take the limit as h approaches 0, x plus h power n minus x power n, something like that. And when you did the calculation, that's in, I think it's on page, probably, let me check, that was on page 12. So check page 12 of the notes. You work out, you end up with this, right? That's n is a positive integer. And only when it's a positive integer, you can expand this, right? When you expand, you get x power n, and then you get n times x power n minus 1h, etc. Something like this. So you can expand because it is a positive integer. All right, and then the next thing we see is, once you prove it's true for positive integer, let's see whether it is true for n equal to -1. And to prove that, again, we can use first principle. Actually, don't need to use first. Actually, use first principle. So that was in the exercise. So if you use first principle, f of x equal to 1 on x, and you take the limit as h approaches 0 of 1 over x plus h minus 1 over x over h. Write this down, and then you make a common denominator. So limit as h approaches 0, x minus x plus h over x plus h. That was not very neat, so we correct it. So you make a common denominator, x plus h over h. And that requires you to do some work because the x gets cancelled. You're left with negative h over x plus h. When you have h in the denominator, you divide it by h like this, and when you divide, you same as. Notice that you have to keep writing the limit until you take the limit. X plus h times by the reciprocal, and that cancels, and you end up with -1 over x. And now you are in a position to substitute h equal to 0. Therefore, you get -1 over x plus 0, which is -1 over x squared, which is -1, -2. So that proves this formula. So that means this formula, if you differentiate x power n, gives you n x power n minus 1, where n is -1. And that formula works. So that proves this formula. And then we've got 2 more steps to go. Then we're done. Yep. Okay. Once it's done, then we can prove it's true for any negative integers. And to prove it's true for any negative integers, that's when you have to prove this. When differentiate, bring the -1 n down, subtract the n by 1, where n is a positive integer. So we want to prove it's true. This is true. To prove this is true, you don't have to use differentiation by first principle. All you have to do is to use the chain rule. So you want to write y x power -n, x power n -1. Remember, n is a positive integer. And using the chain rule, dy on dx, bring the -1 down, x power n -2. Now, this is true because of the above. This is true because of this. This is based on the formula we just proved before. We've just proved that this is true for n equal to Yeah, we have just established that when you differentiate x power -1 gives you this, which is what we're doing. And then we also have established before that when n is a positive integer, that becomes n x power n minus 1 by the chain rule. So therefore, so this is times, and then you go -n x power of -2n times x power n minus 1. And then you add the indices, becomes -n minus 1, which is the formula as required. So everything can be derived from scratch. All right, good. Now we have proved it's true for any integers. Now we have to prove it's true for fraction as well. And that can be proven on the next page. All right, go to the next page, and we're going to prove it is true for any fraction. Okay, all right, for the fraction bit, you have to, so basically we have to prove it's true for 1 over n, and that becomes that. So to prove that, again, we'll let y equal to x power 1 over n, where n is a positive integer. So we're going to raise both sides to power n, like this, right? Raise both sides to power of n. And then instead of doing dy dx, we find dx on dy. That gives you this. And we know that once you get dx dy, we can find dy on dx. That gives you 1 over this, right? And then we just continue. Dy on dx equals to 1 over that. And remember, all you have to do is to substitute y equal to x power 1 over n in there. And we get 1 over n, x power 1 over n, n minus 1. And then you expand this. Actually, you write it as 1 over n times 1 over x power of n minus 1 on n, which is, yeah, okay. So actually, we bring it up, negative n minus 1 on n, and then we simplify x power of -1 plus 1 over n, which is required, as required. Yeah. All right, hopefully you can see, and then we can prove it's true for any rational number. As you can see, for any fraction becomes that. And because we have proven this formula, now we can do that. So we do y equal to x power m over n dy on, before we do that, we write that as 1 over n. And we have got a formula, because m is any integer, we know how to differentiate that. We know how to differentiate that. We just have to use the chain rule. So use the chain rule to prove. Chain rule. And to use the chain rule dy on dx, you get m x power 1 on n, n minus 1, times the derivative of that, we just proven, 1 on n, x power 1 on n minus 1. And if you go through the index law, if you do the calculation, you should be able to get that. I'll leave it as exercise to you. And if you want to know the complete working, check the textbook. And I think it is in exercise. Which exercise would that be? Exercise when we do the rational values. Rational fractional indices 9G. Check the textbook exercise 9G. There's a proof in that section, and you should be able to get that. Yeah, just using index law. Okay, cool. Thanks for that. We're going to start polynomial.